Ladies and gentlemen, what if the survival of our species no longer depended on a single fragile planet? What if the technologies you see shaping electric vehicles, energy systems, and artificial intelligence today are actually rehearsals for something far bigger? This is not about flags on red soil or distant dreams. This is about engineering a future where humanity cannot be erased by one disaster, one mistake, or one moment in time. Every rocket launch, every reusable system, every breakthrough you hear about is pointing toward a single question. Can we design civilization to last beyond Earth? Stay with me because the answer is already being built. And the vision of building a Mars colony is not science fiction, but a carefully engineered extension of humanity's drive to innovate, survive, and expand beyond Earth. It begins with a simple but bold premise. If life is fragile on a single planet, then becoming multiplanetary is not an option, it is a responsibility. This idea drives the collaboration between private innovation and public space exploration, where cutting-edge engineering meets decades of scientific research to solve problems that have never been solved before. And at the core of this plan is the development of fully reusable spacecraft designed to dramatically reduce the cost of space travel. Reusability is not just a technical upgrade, it is a philosophical shift. By treating rockets more like aircraft than disposable machines, spaceflight becomes scalable, repeatable, and eventually accessible. This is essential for Mars, where thousands of missions will be required to transport people, infrastructure, and supplies over many years. Precision landings, rapid turnaround times, and minimal waste define the approach, reflecting an obsession with efficiency and first principles thinking. And a Mars colony cannot rely on constant resupply from Earth. That would be slow, expensive, and unsustainable. Instead, the strategy focuses on in situ resource utilization, meaning the planet must provide what settlers need to survive. Mars offers carbon dioxide in abundance, water, ice beneath its surface, and minerals that can be refined for construction. By combining these resources with advanced chemical processes, fuel, oxygen, and water can be produced locally. This transforms Mars from a hostile destination into a livable system, built step by step through automation and intelligent design. And energy is another cornerstone of the plan. Solar power plays a central role, using lightweight, high-efficiency panels deployed across the Martian surface. Energy storage systems ensure power is available during dust storms and long nights, enabling continuous operation of life support systems, communication networks, and manufacturing units. Every system is designed to be modular, redundant, and resilient, because failure on Mars is not an inconvenience, it is an existential risk. And human life on Mars requires habitats that protect against radiation, extreme cold, and low atmospheric pressure. Early structures are expected to be prefabricated, rapidly assembled, and partially buried beneath the surface for natural shielding. Over time, these habitats evolve into more permanent settlements, using local materials and 3D printing techniques to expand living and working spaces. The design philosophy emphasizes simplicity, durability, and adaptability, allowing the colony to grow organically as more people arrive. And artificial intelligence and robotics act as the silent workforce of the Mars project. Long before humans set foot on the planet, autonomous systems prepare landing zones, assemble infrastructure, and test life support technologies. These machines continue to play a vital role even after human arrival, handling dangerous tasks and optimizing daily operations. The goal is not to replace human presence, but to amplify it, allowing settlers to focus on exploration, science, and long-term planning. And the partnership between private aerospace innovation and a national space agency represents a new model for exploration. One side brings speed, risk tolerance, and manufacturing agility. The other brings scientific rigor, experience, and a deep understanding of planetary environments. Together, they form a system capable of executing one of the most complex projects in human history, driven by data, iteration, and constant improvement. And a Mars colony is not just about reaching another planet. It is about redefining what humanity can achieve when technology, vision, and purpose align. The lessons learned from building a self-sustaining civilization on Mars feed back into life on Earth, improving energy systems, manufacturing methods, and our understanding of survival in extreme environments. The journey to Mars becomes a catalyst for innovation everywhere, pushing civilization forward through relentless problem-solving and an unwavering belief that the future is built, not waited for. And this feedback loop between Mars and Earth is intentional. Every system designed for survival on a distant planet must be ultra-efficient, low-maintenance, and scalable. Those same requirements expose inefficiencies in terrestrial systems that have long been accepted as normal. Closed-loop life support pushes advances in water recycling and air purification. Extreme energy constraints accelerate improvements in battery storage and grid resilience. Even food production on Mars forces breakthroughs in compact, high-yield agriculture that can later address food insecurity on Earth. And transportation between planets follows the same philosophy of rapid iteration and cost reduction. Instead of waiting decades between missions, launches are planned in frequent cycles timed with planetary alignments to maximize efficiency. Each flight is a data-gathering exercise refining trajectories, materials, and operational procedures. Failures are not hidden. They are analyzed, redesigned, and eliminated. Progress is measured not in announcements but in hardware that flies, lands, and flies again. And human selection for early Mars missions emphasizes adaptability over perfection. The environment demands individuals who can solve problems under pressure, learn continuously, and operate across disciplines. Engineers become technicians, scientists become builders, and everyone becomes responsible for system integrity. This cross-functional mindset mirrors the engineering culture behind the program itself, where silos slow progress and integration accelerates it. And communication latency between Earth and Mars introduces a fundamental shift in how decisions are made. With delays ranging from minutes to nearly half an hour, settlers cannot rely on real-time guidance. Systems must be autonomous and people must be empowered to act independently. This drives the development of smarter onboard software, predictive maintenance algorithms, and decision support tools that can anticipate problems before they become critical. Autonomy becomes not just a technical feature but a survival requirement. And psychological sustainability is treated with the same seriousness as physical survival. Long durations in isolation, confined spaces, and a hostile environment require intentional design choices. Habitats incorporate natural light simulation, flexible living spaces, and visual connections to the surrounding landscape. Work schedules balance productivity with mental health, recognizing that long-term success depends on emotional resilience as much as engineering excellence. And as the colony grows, specialization increases. Research labs focus on planetary science, geology, and the search for past or present life. Manufacturing hubs begin producing replacement parts and tools, locally reducing dependence on Earth shipments. Over time, the colony shifts from a fragile outpost into a robust node of human civilization, capable of supporting itself and expanding further. And governance on Mars evolves pragmatically. Early rules prioritize safety, resource allocation, and mission success. Over time, social systems emerge organically, shaped by necessity rather than tradition. The emphasis remains on transparency, accountability, and evidence-based decision-making, reflecting the engineering mindset that built the colony in the first place. And the economic model of a Mars settlement is not driven by short-term profit. Its value lies in long-term survival, technological spillover, and the creation of an insurance policy for humanity. By proving that a self-sustaining civilization can exist beyond Earth, the project redefines risk itself. Extinction-level threats become challenges to engineer around, not inevitabilities to fear. And every step toward Mars reinforces a larger idea. Progress accelerates when ambition is matched with execution. The colony is built not through grand declarations, but through thousands of small decisions optimized for performance, cost, and reliability. Each component exists for a reason. Each system is tested against reality, not optimism. And in the end, Mars is less a destination than a proving ground. It tests whether humanity can apply its intelligence deliberately, whether technology can be aligned with long-term thinking, and whether civilization can evolve beyond short horizons. The effort reshapes how exploration is defined, turning it from symbolic achievement into practical expansion driven by engineering discipline, relentless iteration, and the conviction that the future must be actively constructed. And this proving ground also reshapes how risk is perceived at a civilizational level. Traditional exploration minimized risk by limiting scope, cost, and ambition. The Mars Initiative inverts that logic by acknowledging that the greatest risk is stagnation. By engineering systems that expect failure and recover quickly, resilience is built into the architecture from the beginning. Redundancy is not waste, it is insurance. Simplicity is not limitation, it is robustness. Every design choice is filtered through the question of whether It can survive repeated use, unexpected stress, and long durations without human intervention. And materials science plays a critical role in this transformation. Lightweight alloys, heat-resistant composites, and advanced ceramics are selected not just for performance, but for manufacturability at scale. The same thinking that reduces mass and increases strength in space hardware also translates into more efficient products and infrastructure on Earth. When materials are optimized down to their atomic properties, cost curves shift, and new possibilities emerge across industries. And thermal management becomes a defining challenge on Mars, where temperature swings are extreme and unforgiving. Systems must retain heat efficiently, while preventing overheating during operations. This drives innovation in insulation, phase change materials, and smart thermal control technologies that later influence energy efficiency in buildings, vehicles, and data centers. Mars does not allow inefficiency to hide. Every wasted watt is exposed. And the data generated by continuous operations on another planet feeds an unprecedented feedback system. Sensors embedded in every structure, vehicle, and life support unit stream performance metrics that refine models in real time. Machine learning systems detect anomalies, predict component wear, and recommend design updates. Engineering becomes a living process, constantly informed by reality rather than static assumptions. And education within the colony evolves alongside its infrastructure. Training is continuous, adaptive, and deeply practical. Knowledge is shared openly because survival depends on collective competence. This culture of radical transparency and shared problem-solving mirrors the engineering philosophy that prioritizes learning speed over hierarchy. Authority comes from understanding systems, not titles. And over time, cultural identity on Mars begins to diverge naturally. Daily life is shaped by constraints that encourage efficiency, cooperation, and long-term thinking. Waste is unacceptable. Energy awareness is instinctive. Decisions are evaluated not just for immediate benefit, but for their impact on system stability years into the future. These values, forged by necessity, offer a counterpoint to short-term consumption-driven models elsewhere. And scientific discovery remains a constant driver. Mars provides a record of planetary evolution that Earth can no longer offer in pristine form. Studying its geology, climate, history, and chemistry deepens understanding of how planets change and what conditions allow life to emerge. This knowledge feeds back into planetary defense, climate modeling, and the search for life beyond the solar system. And as interplanetary logistics mature, the concept of distance itself begins to change. What once took months of planning becomes routine. Supply chains stretch across millions of kilometers, coordinated by software that optimizes timing, payloads, and energy use. This capability does not remain isolated to space. It influences global logistics, manufacturing, planning, and infrastructure resilience on Earth. And the presence of humans on Mars also reframes ethical questions about exploration. Responsibility extends beyond arrival to stewardship. The environment is treated with scientific respect, contamination is minimized, and exploration proceeds cautiously. The goal is understanding, not exploitation, guided by evidence and long-term preservation. And what emerges from this effort is not a singular achievement, but a new operating system for civilization. One that favors iteration over inertia, data over assumption, and durability over spectacle. The Mars colony becomes a reference point, demonstrating that complex systems can be designed to serve long-term survival rather than short-term reward. And each launch window, each assembled habitat, each solved problem reinforces a deeper confidence in applied intelligence. The project proves that constraints, when embraced rather than avoided, become engines of creativity. Scarcity sharpens focus. Distance demands autonomy. Hostility forces cooperation. And through this lens, Mars is not distant at all. It is an extension of a mindset that refuses to accept limits without testing them, that reduces impossibility to a set of solvable problems, and that measures success by what works in reality. The colony grows as an accumulation of disciplined choices, relentless testing, and systems that improve because they are used, challenged, and rebuilt again and again. And that continuous rebuilding mentality gradually reshapes how time horizons are defined. Decisions are no longer optimized for quarterly results or short political cycles, but for decades and centuries. Infrastructure is planned with the assumption that it will be expanded, modified, and reused by generations who have not yet been born. This long-view engineering approach changes priorities, favoring durability, upgrade paths, and open-ended design over fixed, closed systems. And population growth on Mars is managed deliberately. Early phases prioritize stability over scale, ensuring that life support energy production and food systems consistently outperform demand. Growth only accelerates when margins are proven in real conditions, not simulations. This disciplined pacing avoids cascading failures and reinforces a culture where expansion is earned through performance. The colony grows because it works, not because it was promised. And healthcare in a low-gravity, high-radiation environment drives innovation in monitoring and prevention. Continuous biometric tracking enables early detection of issues before symptoms appear. Exercise systems are integrated into daily routines to counteract muscle and bone loss, while medical protocols emphasize prevention over treatment. These advances ripple back to Earth, influencing remote medicine, wearable health technology, and personalized care models. And children born on Mars represent a profound shift. Education is immersive, hands-on, and system-focused from the beginning. Physics is not abstract. It is visible in every airlock and power circuit. Biology is lived daily through closed-loop ecosystems. This environment produces a generation fluent in complexity, comfortable with responsibility, and deeply aware of interdependence. Learning is inseparable from survival, embedding competence as a cultural norm. And manufacturing capabilities evolve from basic fabrication to advanced production. Metals refined from Martian regolith, plastics synthesized from atmospheric carbon, and electronics assembled from imported high-value components reduce dependency on Earth. Over time, supply chains invert, with Mars exporting specialized data, research, and designs rather than physical goods. Value becomes informational, not material. And the psychological relationship with Earth also changes. Initially, Earth represents safety, abundance, and origin. As Mars matures, it becomes a peer, a second home rather than a backup. Communication delays remain, but emotional distance shrinks as shared culture, goals, and identity solidify. Humanity no longer belongs to a single planet by default. And environmental engineering on Mars extends beyond survival into optimization. Terraforming is not an immediate objective, but incremental modification of microenvironments demonstrates what is possible. Controlled atmospheric changes within habitats, localized warming, and biological experimentation inform long-term models. Every experiment is cautious, reversible, and data-driven, prioritizing understanding over speed. And security on Mars is redefined. There are no borders to defend in the traditional sense, but system integrity becomes paramount. Cybersecurity, redundancy, and fault isolation protect against cascading failures. Cooperation is not optional, it is enforced by physics. Conflict wastes resources, and waste threatens survival. Stability emerges from shared dependence rather than imposed authority. And as experience accumulates, the Mars framework becomes a template for expansion beyond Mars itself. The same principles apply to lunar bases, asteroid mining operations, and deep space research stations. Mars serves as the first full-scale test of a distributed, resilient, multiplanetary civilization. Each new node benefits from lessons learned, shortening development cycles and reducing risk. And public perception of space shifts as well. What was once distant and symbolic becomes practical and relevant. Young engineers, scientists, and builders see a clear path from education to contribution. Space is no longer reserved for a few. It becomes an extension of industry, research, and daily life. Inspiration is grounded in participation, and the economics of scale begin to take effect. As launch costs drop and production ramps up, barriers to entry fall. Innovation accelerates because iteration accelerates. Competition improves systems, collaboration standardizes interfaces, and the overall pace of progress increases. The ecosystem grows stronger through use, pressure, and continuous refinement. And all of this reinforces a central realization. Civilization advances most effectively when it treats reality as negotiable through effort. Mars does not reward hope or intention. It responds only to what is built, tested, and improved. This feedback is unforgiving but honest, stripping away illusion and replacing it with clarity. And the colony exists because countless problems were broken down, prioritized, and solved under real constraints. It persists because those solutions are constantly questioned, measured, and upgraded. In that process, humanity proves not just that it can reach another planet, but that it can redesign itself around competence, responsibility, and long-term survival expressed through systems that work because they must.